This is a very standard exponential growth problem. A bacteria culture grows with constant relative growth rate, okay? So, meaning the relative growth rate, that's the K, okay? The bacteria count is 400 after 2 hours and 25,600 after 6 hours. So then they ask you all these questions. All of them you can answer as soon as you know what K is, right? Because if it has a constant relative growth rate, that's going to tell you that Y of t is Y naught e to the kt. So it's all these things are based on that equation, okay? So we can figure, so Y naught is the initial population. They didn't give us that, but we can figure that out. In fact, that's one of the questions, right? Actually, that's the second question. So, but the first question is, what is K? Which is always going to be the first thing to figure out, right? So, what is the relative growth rate? So you have two different points, right? You know that this guy is Y and this guy is T. So you know that Y at 2 is 400, and you know that Y at 6 is 25,600. Okay, so we can just use these two equations. So we have two equations, and we actually have two unknowns, right? We have Y naught and K. So this would be e to the 2K, and then at 25,600, it's Y naught e to the 6K, right? Because it was T equals 6. Okay, so notice I can kind of eliminate the Y naught, right, by dividing. So I've got 400 over e to the 2K is Y naught, and then on this second one, I'm going to have 25,600 over e to the 6K. So let me kind of put this all together. I end up with 25,000 over 400 here, and this should be e to the 6K over e to the 2K, or e to the 6K minus 2K, right? So this is just, what's 256 divided by 4? It's 64. Okay, that's just 64. And this is e to the 4K, right? So e to the 4K equals 64. I take the natural log of both sides. I get 4K equals ln of 64. And that gives me what K is. K is 1/4 natural log of 64. And you can use it in that form, or you can use a decimal form. So it actually works out to be 1.04. And sometimes they want that as a percentage, so then it'll be 104%, right? So obviously this thing is getting big fast, right? It is a bacteria culture, after all. That is what we'd expect. So let me put this in here. I'll just write it up here. K equals 1/4 ln 64, which is 1.04. So that is our first, where's my thing? Well, that is the first problem, right? So the relative growth rate K is 1.04. Now my second question is, what is the initial size of the culture? So I can use either of the 2 points that I had to figure out what Y naught is. So I'll use the first one, right? Y of 2 is 400. Now we know what this K is, and this time I'm just going to use, so 2 times 1/4 natural log of 64. So you could just really do this with decimals if you want. It just happens to that they picked numbers that are cute. So we'll do it that way because it's nicer. Y naught e to the 1/2 natural log of 64. Okay, so what is that? E to the 1/2 natural log of 64. I pull up the 1/2, so I get e to the natural log of 64 to the 1/2. So e to the natural log of 8. So this is just 8, right? So I end up with 400 equals 8 Y naught, which is Y naught equals 50. So that's what I started out with, my initial population y naught equals 50. So in fact, if I want, rather than keep this up here, what I'm going to do is I'm just going to write, and that's actually part of that's number 3, right? Number C, find the population. It's going to be 50 e to the t times 1.04. And so that's what it is, right? That's the formula for the population. So now I can answer all the rest of the questions they happen to throw at me because I know what the population is at any time t. So let's go. Find the number of bacteria after 4.5 hours. Okay? By the way, it is true that the t is in hours because we started everything in hours. And then the number of bacteria is just that population. So for part D, I'm just going to do y at 4.5. So 50 e to the 4.5 times 1.04. And I did this. We can find it. So what the heck is it? Okay, I can't read my own writing. It looks like 5,385. 89? 89. Something like that. Anyway. Then that's the second question, almost the last question, right? Find the rate of growth at 4.5 hours. So this is a sort of a silly thing. Like the reason K is called the relative growth rate is because really what is the rate of growth? The rate of growth is dy dt, right? So it's the change in population over the change in time. That's the growth rate, dy dt. That's what they want. So, but you know what that is, right? It's ky. So all I have to do is put in my k, which was 1.04, times my y at 4.5, which we just found. So that is, when you multiply that, this is 5604. And what are the units? The units are going to be bacteria per hour, right? Because the population is the number of bacteria. Okay, so at this time, at time 4.5 hours, the population is changing by 5,604 bacteria per hour. But that's an instantaneous rate of change, right? That's at exactly 4.5 hours. So, last question, when will the population reach 50,000? So for 50,000, we're going to solve for the t that gives us y equals 50,000. So I'm just going to put it in there. 50,000 is 50 e to the t times 1.04. Right? So that just gives me 1,000. Divide that through. Equals e to the t times 1.04. Natural log of both sides. Natural log of 1,000 equals 1.04 t. And that gives me t being whatever this was, 1,000 over 1.0. I gotta get this thing here. Where is it? Yeah, natural log. I'm like, something's wrong because that's not the right answer. I lost the natural log when I rewrote it. Natural log of 1,000 over 1.04. And this is, let's see here somewhere. Oh, here it is. I have to write these better. 6.642 hours. And that makes somewhat sense, right? Because we know that by 6 hours, you're up to 25,600. So obviously 50,000 is going to be more. So 6.5, right? At 4.5, you're here. But it's, of course, exponential growth. It goes faster and faster. I mean, the relative rate is the same. But if you look at the steepness of the curve, it goes up high. That's what I meant.